Dear students, today we will be discussing about solar pond. Basically, we will study salt gradient solar pond. This salt gradient solar pond is an economical way of collecting and storing of solar energy requiring low temperature process, and it can provide process heat at a temperature of 70 to 80 degree C in an average. So, first let us learn what is solar pond. A solar pond is a pool of salt water which collects and stores solar thermal energy. The salt water naturally forms a vertical salinity gradient in which low salinity water floats on top of high salinity water. The layers of salt solutions increases in concentration with depth. Below a certain depth, the solution has a uniformly high salt concentration. So, pictorially it can be represented something like this. Here solar radiation is receiving and it transmits through these layers and it receives at the bottom and it is retained because this salt gradient is maintained. So, what is the difference between these solar pond and normal pond? In case of normal pond, what happens? This solar radiation received from the sun, and then as soon as it receives at the bottom, so what happens? A convection or convective current is generated. Because of that, this temperature difference between this top layer and this bottom layer is very less. Here in this case, what happens? Salt is applied to reduce this convective current, so that the amount of heat which is retained at the bottom or received at the bottom can be retained for other applications. Okay? So, this is nothing but solar energy collection and storage. Okay? Once we can heat or we can have high temperature here, we can collect it for applications required for a particular process. So, let us discuss some of the facts related to solar pond. The first solar ponds were constructed in Israel in the early 60s by Tabor and his co-workers. A maximum temperature of 100 degrees C were obtained at the bottom. Many practical difficulties were encountered and the work was abandoned. The number of solar ponds have been built all around the world to utilize the stored heat for providing process heat and generating power. The largest solar pond was installed at Israel and it covers an area of about 250,000 meters square. That heat what is generated there is used to generate electricity by using an organic Rankine cycle. Mostly what we can see in these applications are restricted to desalinations and brine management. In Australia, they use this kind of system to supply heat in salt production process in a place called Pyramid Hill. In India, we have a solar pond at Bhuj, Gujarat, and it covers an area of 6,000 meters square, and this is used to supply process heat to a dairy farm. So, this is a photograph of the plant which is installed at Gujarat. Now, let us learn the working principle of solar pond. How does a solar pond works? So, here what is shown, let us consider a pond of depth L. So, it is going towards x direction and this is the depth of the pond L. Okay? And let us consider the concentration of the top layer is C1 and concentration of the bottom layer is C2. So, there is a concentration gradient. So, this C1 is less than C2, okay? Concentration of brine, right? Now, if I am interested to see the variation of density and temperature at these concentrations, how it will look like? So, it will be something like this. So, this vertical axis shows the density and then horizontal axis shows the temperature variation, right. So, if we consider the C1 is the concentration for the top layer and C2 is the concentration for the bottom layer, right. So, here rho 1 and T1 is the density and temperature at point P where this C1 meets, okay. And then rho 2 and T2 are the density and temperature at the bottom layer, right. And there will be something like this kind of profile of variation of density with respect to temperature. So, we can have multiple points in between this top layer and bottom layer, and then we can find out what will be the exact values of this density at particular temperature, right. So, what we can understood here, no convection will occur so long as the slope of the curve PQ is positive, okay. So, if this curve is positive, so convection will not occur, so there will be a concentration gradient, right. So, which is required for a solar pond. Now, mathematically we can represent this d rho by dx greater than 0. That means what? Density at the bottom layer is always more than the just above layer, okay. So, this rho density of the brine solution is a function of concentration and temperature. So, we can apply the total differentiation. D rho is dou rho by dou C at constant temperature is dC plus dou rho to dou T at concentration is dt. Then if we divide the above expression by dx, so it will be something like this, okay. Now, if we apply the equation 1, then d rho by dx is equal to this portion, okay, which is greater than 0. Now, if I am interested to develop the expression in terms of dC by dx, the concentration gradient along the depth, then we can develop it. D rho by dx will be something like this. So, this equation may be A I can write here, okay. Or in a very involved way, if we consider the momentum diffusivity, then thermal diffusivity and mass diffusivity, this is the mass diffusivity, mass diffusion will be there because if salt is there at the bottom, okay. So, salt is here and then mass diffusion will takes place, okay. Because of that we need to consider this mass diffusivity D, and this nu is momentum diffusivity and this alpha is thermal diffusivity. So, this is thermal, mass, and this is momentum diffusivity, okay. So, this value as per the experimental observations, it is found to be 1.15. So, dC by dx greater than 1.15 times this expression, okay, to be precise. Normally this is also considered as 2, okay. So, if we have to make a design, so some kind of margin we have to maintain. So, this expression need to be multiplied by 2, then what we can get the dC by dx stability criteria, okay. So, calculation of minimum concentration gradient required for maintaining a given concentration gradient at a particular level in a solar pond can be calculated by using either of these equations, okay. So, this is very important. So, once this stability criteria is established, then it is found that things will work perfectly as designed. So, let us take a small example about this concentration to understand in more deeper sense. Like sodium chloride is used as a salt in a solar pond. Estimate the minimum concentration, that is kg of salt per kg of water required at the bottom if the concentration at the top is given as 0.02 and the temperature difference of 65 is given, and that has to be maintained. Assuming the concentration and temperature profiles are straight line, and take the average value of dou rho by dou T and dou rho by dou C to be minus 0.5 kg per cubic meter per degree centigrade and 650 kg per cubic meter respectively, then we can calculate the minimum concentration. We know the stability criteria, something like this: d rho by dC greater than dou rho by dou T multiplied by dt by dx, then dou rho by dou C at constant temperature. So, we can substitute the values given in the problem. So, So, this is 0.5 dt by dx, and then we have 650, then 650 is the density, and then dc is something like this with simplification, and then C2 minus C1 is the concentration at the bottom part minus top, and then we can have this expression, and finally what we will get C2 is 0.02 kg of salt per kg of water. Okay. So, this is how we can calculate the concentration gradient required for this kind of analysis. Now, let us learn the working principle. So, here as you can understand now, in case of solar pond there are 3 layers. Upper layer is called upper convective zone, or sometimes it is called surface convective zone, and middle layer is the non-convective zone. The bottom layer is called lower convective zone, okay, where this part is the storage and collection, and middle part is something like insulation, so that no convection current is generated, and most of the heat what is fallen here is lost to the environment. These are the heat, okay. Some kind of evaporation losses will be there, and then heat interaction from the ambient is there. So, it is shown that the energy is falling from the sun, it is received at the bottom, and then this convection current is resisted by this salt gradient. Okay. So, let us learn one by one. This surface convective zone or upper convective zone is very less thick. So, it is about 10 to 20 centimeter, and the concentration is uniform, and temperature is also uniform. Because of that we can have just a line here. So, concentration and temperature is something like constant. And in the non-convective zone, half of the depth of the pond normally considered as this non-convective zone. So, if it is total depth is 1 meter, so 0.5 meter is for non-convective zone, and temperature and concentration increases with depth. So, this variation will be something like this. So, temperature and concentration will vary in this zone, and this zone acts as insulating layer and reduces heat losses in the upward direction. Role of this zone is very crucial for successful operation of a salt gradient solar pond. And the third zone is lower convective zone. This part is the lower convective zone, where temperature and concentration is constant, and this part is serve as main heat collection as well as thermal storage medium. Okay. So, heat will be stored here, and then from the here heat has to be collected, okay, by installing some kind of heat exchanger or maybe organic Rankine cycle if electricity generation is the prime activity. Okay. So, this is the pond. So, this is the upper temperature and concentration, and what happens here, sometimes we need to provide fresh water here to maintain the salinity gradient. So, when we provide fresh water, along with this salt is also moves, okay, salt is also moves, and then in order to use this salt again, then we need to have a separate plant to evaporate the water present, and then we can separate salt and water, and then that salt can be used here again to maintain the salinity gradient. Okay. So, this depth is typically 2 to 3 meter, and here this black colored things what is shown, this is nothing but a thick durable liner normally composed of low density polyethylene or LDPE or high density polyethylene HDPE or woven polystyrene yarn, which are attached at the bottom in order to reduce the heat losses. And the kind of salt used for this kind of arrangement is magnesium chloride or maybe sodium chloride, and this concentration varies from 20 to 30% at the bottom to the 0 at the top. Okay. This concentration need to be maintained. The temperature of the lower layer may rise to as high as 95 degrees C in summer. For winter it is about 60 degrees C, and this salt requirement is about 50 gram per meter square per day, okay, which is really a significant amount if we consider for a yearly operation. So that's why this evaporation of this water when fresh water is added and then reuse of the salt is very, very important. The annual collection efficiency varies from 15 to 25%, which is less than the flat plate collector. Okay, and cost per square meter is much less than the flat plate collector. So this is a very, very economical way of collection and storage of thermal energy. And this arrangement, what is shown here is use of solar pond for power generation. So here what happens, collection and storage will be there, and then we can circulate cold brine and then hot brine will move out, and there will be heat exchanger. Okay, heat will exchange from this hot brine to the organic fluid used in the secondary cycle. So this may be ammonia. Okay, so this organic fluid takes the heat from the brine and it is evaporated, and then it is expanded in the turbine and electricity can be generated, and this eject of this turbine is cooled by using a condenser cooling tower assembly, and of course here we need a pump to circulate the fluid again and again in the closed loop. So these pumps here also we need a pump. So this figure shows the working of a solar pond for power generation application. Now let us analyze the performance of a salt gradient solar pond. So for that we need to understand the transmissivity based on reflection and refraction at the air water interface, because we have air and water. This is the pond, and we have air here and we have water here. Okay, so this is the air water interface. So we need to know the transmissivity based on the reflection refraction and also transmissivity based on refraction. Okay, already we have studied the cases when there is a air and glass in case of flat plate collector. Okay, so what happens, the incident beam falls on this transparent cover and then it is reflected, okay, and it is refracted. So we know the relationship between theta 1 and theta 2 by using the Snell's law. Okay, same principle can be applied here. So if we know the reflective indices of water with respect to air, which is nothing but 1.33. Okay, so if you know this 1.33 and theta 1 is known, then theta 2 can be calculated. So same principle what we have followed for design of a flat plate collector can be applied here. And also we know these two components of polarization. So if we know these two components of polarization for reflection, so this is rho can be calculated, and then if we know rho, then again we can use the same methodology for calculation of tau r. So this is transmissivity based on reflection and refraction, and this tau r1 and tau r2 are the two components of the polarization. Now here people have done lot of research and they have found these kind of observations. So by varying these angles of incidence from 0 to 70, and then this theta 2 can be calculated because n2 by n1 is known, that is 1.33. So if we do this, so this kind of data can be generated, and we can get the values of tau r at different incidence angle. Okay. So as you can see, when incident angle is increases, so this tau r is reduces. So it is more significant if we go beyond 75, and at 90 it is almost 0. Okay. So at higher angles this is not encouraged. For angles of incidence from 0 to 60, the loss due to reflection is small, that is 2 to 6%. For large angles, the loss is large. Okay. So which is not interested because these are associated with low values of radiation. Okay. Now let us analyze on transmissivity based on absorption. As we know, this expression Bogart's law, di is proportional to I, okay, and dx, and this k is the constant. Okay, this is known as extinction coefficient. Okay, and we can have a solution of something like this. So we can get the value of transmissivity based on the absorption by using this expression. But this cannot be used directly here because this k extinction coefficient is a strong function of wavelength. So this wavelength has been considered by authors like Nelson and Rebel, and they found this kind of correlations. Tau A is equal to e to the power of minus kj into x. X is nothing but the depth of the water, and these A values at different conditions were calculated. These are the fitting coefficients, okay, and this A1 is valid for this range of wavelength, and A2 is valid for this range of wavelength. So similarly, A3 and A4s are valid for a range of wavelength. Okay. So if we combine this A1, A2, A3, A4, and if we analyze critically, it is found that about 77.6% of radiation is accounted corresponding to wavelength of 0.2 to 1.2. This is 0.2 to 1.2 micron, and this balanced 22.4% corresponds to the radiation wavelength greater than 1.2 micron, which is absorbed near the surface 1 to 2 centimeter from the surface. Okay. Also we can use this kind of correlation, which is very simple, developed by Bryant and Kolbeck. So this is the expression where x is the depth of the water, which is in meter, and this is valid for x has to be greater than 0.01 meter, and this expression is valid when solar radiation is falling normal to the horizontal surface. So if it is inclined, then we need to express the correlation something like this. It will be x by cos of theta 2. So we must know what is theta 2, right. So these expressions need to be applied for calculation of transmissivity based on absorption. Now let us take an example. It goes something like: a 2 meter deep solar pond is built in Guwahati. Its latitude is given 26 degree 8 minute. The values of global and diffuse radiation measured on a horizontal surface on 15th May at 1300 local apparent time or solar time are 900 watt per meter square and 200 watt per meter square respectively. Calculate number 1 flux reflected from the water surface, number 2 flux entering the water, and number 3 solar flux at the depth of 0.01, 0.51 and 2 meter. So on May 15th, the n is equal to 135, you can calculate it, right, and phi is 26 plus 8 by 60, it will be degree now, 26.13 degree. So if you know n, then straight away you can calculate what will be the declination. So delta can be calculated by using this expression, and now next step we need to calculate what is theta 1. Okay. So this theta 1 is related with this expression, and phi is already known, delta is known here, and omega here it is 1300 local apparent time means minus 15. Okay. So we can substitute those values here and we can find out what is theta 1. So theta 1 will be about 15.667 degree. Okay. So once we know theta 1, then we can calculate what is theta 2 by using the equations. So sin theta 1 by sin theta 2 is mu 2 by mu 1. So this is 1.33. So theta 2 is about 11.715. Okay. So we can use the chart to know this rho b for beam radiation and for diffuse radiation. This is for diffuse radiation. Theta 1 is 60 we have considered, and theta 2 is 40.62 and rho d is 0.059. From where we got this? We got this from this table. Okay. So as you can see, this is 15. So theta 1 is about 15.67, it is close to 15, and then theta 2 is about 11.71. So it is very close by. So we can take a value of 0.020 for rho. Okay. And for diffuse radiation, since we can consider, so when solar radiation is falling at an angle of 60 degree, so that can be considered as diffuse radiation. Okay. That is why this theta 1 is considered as 60. Okay. So under that condition, theta 2 will be 40.63, and then we can get a value of rho is equal to 0.059. Okay. So with these values we can calculate the flux reflected from the water surface. So, this is flux reflected from the water surface. So, how we can calculate? We know this rho b now and rho d, and I b is known because I g is given. I g is given as 900 watt per meter square. So, what will be I b? So, I b will be 900 minus 200 because I d is given as 200 watt per meter square. So, it will be 700 watt per meter square. So, that way we can get what is I b. I b is 700, and then I b rho b is 0.02 plus 200 into rho d is 0.059, which is equal to 25.8 watt per meter square. Now, this flux entered the water, that means this is reflected back. Okay. So, 900 is the amount of solar radiation, that is global radiation falling on the solar pond. So, 900 minus 25.8, it will be 874.2 watt per meter square, which is entering in the water. Now, we need to calculate the transmissivity based on the absorptions. So, we can use this equation, okay, so which is known to us now. So, once we substitute the value of theta 2 and x for a particular case, so we can calculate what will be the reflectivity based on the absorption. So, we can develop this chart, and equations are known. So, if we consider for beam radiation, it will be tau a b. Okay. So, theta 2 will be 11.715 degree, and if we do the calculation, it is found to be 0.7262. Then at x is equal to 0.5, it is 0.4135. X is equal to 1, it will be 0.3583. X is equal to 2, it will be 0.3028. Okay. Similarly, for diffuse radiation, this is tau a d, and theta 2 will be 40.63 because theta 2 is required here, and different values of x, we can calculate what is tau a d. Okay. So, these are the values we got for diffuse radiation. What is the next step? So, next step is to calculate the solar flux at various depth. So, what will be the solar flux at x is equal to 0.01, x is equal to 0.5, x is equal to 1, and x is equal to 2 meter. Okay. So, this is the expression we can use, and these values are known to us. So, tau r b, how to calculate? Because rho b is known, okay, then 1 minus rho b will be your tau r b. Okay. So, similarly, rho d is known, okay. So, 1 minus rho d will be tau r d. Okay. So, that way we can consider and we can calculate, and it is found to be something like this. Okay. So, at various depths, the solar flux received will be something like this. So, we can plot it, how the solar flux varies at different depth. Okay. So, if we plot it, so what kind of conclusion we can draw? So, we can develop this kind of plot. Okay. So, this water depth is here, and then solar flux is in the horizontal axis, right. So, if we say 900 is watt per meter square is the incident flux, and then after considering the reflection, it will be 874 watt per meter square is entering into the water, and then what happens, it reduces, and then finally the amount of solar flux received is about 200 something. Okay. So, which is calculated in the last slide. So, it is when it reaches about 260.86. Okay. Now, if we see for this case, it is considered that the surface convective zone or upper convective zone is about 10 centimeter, and radiation absorbed in the wavelength is about 1 to 2 micron, right, and about 269 watt per meter square, that is 30% of the incident energy is absorbed in the solar convective zone. Since we have considered 10 centimeter, so that much of energy we can deduct from the amount of energy what is available. So, that much of energy is absorbed in the solar surface convective zone, and this energy is almost entirely lost to the surroundings, and this is the reason for low collection efficiency. Okay. So, this energy is almost entirely lost to the surroundings, and this is the reason for low collection efficiency. And this flux which is penetrating to the bottom of the pond is about 261 watt per meter square, which is about 31% of the incident energy. Okay. So, that much of energy is utilized for generation of hot water or maybe generation of electricity, right. Now, we are interested about temperature distribution and collection efficiency. So, if we consider these layers, this is surface convective zone, non-convective zone, lower convective zone. As you know, this temperature and concentration is constant in this zone, and then there is a variation of temperature and concentration in the non-convective zone. Again, it is constant in the lower convective zone, or where collection and storage taking place, right. So, this is the profile, and if we represent this L1 is the thickness of this surface convective zone, and L2 is the depth from the surface to the end of the non-convective zone, and L is the depth of the pond. Okay. So, now how to proceed for investigation of temperature distribution and collection efficiency. So, for an exact solution, one has to solve the appropriate differential equation for each zone, and the matching condition has to be used at the interfaces between the zones and satisfy the boundary conditions at the top and bottom surface of the pond. And assumptions are something like the upper convective zone and the lower convective zone are assumed to be perfectly mixed layer at uniform temperatures, which changes only with time. And second assumption is the lateral dimensions of the pond are large compared to the length, and this temperature varies only in the vertical direction, and properties are constant. So, if we develop the differential equation for non-convective zone, it is represented something like this. So, this di by dt is the solar radiation which is absorbed in the pond, and is the amount of energy which is stored, and is the conductive heat transfer in the non-convective zone. And this I can be represented by using this expression. Already this is done in the problem what we have discussed. And now we are interested about energy valence for upper convective zone and lower convective zone. So, this is the expression for upper convective zone. So, this rho L1 Cp dt1 to dt at x equal to L1, this represents the rate of change of energy contained in the surface convective zone of thickness L1, and this k dt by dx is the rate at which heat is conducted from the non-convective zone, and this I naught and I x equal to L is the solar radiation absorbed in the thickness L1, and this part is the rate at which heat is lost from the top surface by convection, evaporation and radiation. Okay. So, from the top, if we draw this something like this, so from the top we will have conduction losses, evaporation losses, and then radiation losses or convective losses. This is convective losses, not conduction losses. Okay. Now, if I am interested for lower convective zone, so equation will be something like this. So, this part shows about rate of change of energy contained in the lower convective zone of thickness L minus L2, and this is the rate at which heat is conducted in from the non-convective zone. So, this is the conduction part, and this is the solar radiation absorbed in the thickness L2, and this kg dou Tg by dou x is something like rate at which heat conducted out of the ground underneath, and Q load. So, where this in the lower convective zone, this load is like our utility, this Q load, this is the rate of useful heat extraction, is represented by Q load by AP. So, these are need to be studied critically to investigate the performance of a sol gradient solar pond. And also we can develop the annual collection efficiency and extraction temperature, which is a function of pond depth. Okay. So, this figure shows about the variation of annual collection efficiency with pond depth. So, this is something like this. So, as pond depth increases, annual collection efficiency actually increases, and this mean extraction temperature is decreases with increase in pond depth. So, there are applications of solar ponds, like we can have combined system of thermosiphon and thermoelectric modules to generate electricity from solar ponds. Okay. So, here what happens, this is the thermoelectric part, this temperature difference is utilized to generate electricity, and this is the collection and storage part, okay, from where useful heat gain can be extracted and applied as per the application. And here what you can see is the electric power generation from solar pond using organic Rankine cycle. So, here is the low salinity layer, then gradient layer, then concentrated layer. What happens here? So, sometimes we have to apply fresh water, and then when we have to take this saline water out, it contains saline or say salt, and that has to be separated, and that can be again applied in the other layers to maintain the salinity gradient. And the amount of heat what is collected from this lower convective zone, that is used for generation of electricity by using organic Rankine cycle. And this is one of the applications which is used for generation of distilled water. Okay. So, this is the solar pond, and this hot water is supplied to this solar still, and here what happens, evaporation and condensation takes place. First evaporation, because of this temperature difference, again condensation will be there, and that can be collected. So, distillate can be collected by using this system, and this is nothing but an active solar system integrated with a solar pond. And there are some operational shortcomings of solar ponds, like wind induced waves. If wind is there, means there will be waves. So, what will happen, there will be mixing of layers. So, if wind is very high, it is not good for the solar pond. And effect of rain is important. If mild rain is advantageous, if it is a heavy rain, then it is not advantageous. Okay. So, dilution will take place, because no salt will be diffused from the bottom, and then it will be diluted. So, the concentration gradient will not exist. And then biological growth will be there. Okay. Sometimes if it is a stagnant water, then biological growth, algae will be developed. So, this needs to be cleaned periodically to increase the transmissivity. And fouling due to dirt and leaves, because leaves falls and it accumulates at the bottom, and that reduces the efficiency of the solar pond. And effect of bottom reflectivity is also important, and we have to reduce the reflectivity to increase the collection temperature. And there are another kind of solar pond called solar gel pond, and this gel pond is what happens, a thick layer of polymer gel floats on the lower convective zone and act as non-convective zone. This gel is nothing but 98.3% of water and 1.7% polyacrylamide, has a very good optical and thermal insulating properties. And this project demonstrated at New Mexico, where surface area considered was 400 meter square and depth considered was 5 meter, and a small concentration is necessary to float the gel on the top of lower convective zone has been observed. The gel was kept in thin transparent plastic bags made from Tedlar and floated on the salt solution. The thickness of gel is about 0.6 meter and is designed to supply a minimum of 1 gigajoule heat per day at 70 degree Celsius. So, if you compare this solar gel pond and sol gradient solar pond, so it is advantageous, because evaporation loss from the surface are eliminated, then maintenance requirement reduces, the environment hazards associated with handling salt are eliminated. So, these are the advantages of solar gel pond. So, solar ponds across the globes, so these are some of the installations, like solar pond installed at Israel, its capacity is 150 kilowatt, is shown here, and second figure is for solar pond in Gujarat in India, and third photograph is for ORC operated solar pond on Alice Springs in Australia. So, now we can summarize what we have discussed today. We have discussed fundamentals and working principle of solar ponds, which is very important and economical way of collecting and storing solar thermal energy. And also we have studied the temperature profiles and energy balance at different layers, because it composed of 3 layers: surface convective zone, then non-convective zone, and lower convective zone. Okay. And maximum temperature during summer and winter are reported to be about 95 degrees C and 60 degrees C respectively in India. And we have also discussed some of the operational shortcomings and type of solar ponds and applications. On the top of it, we have studied the stability criteria, how to calculate the minimum concentration to operate a sol gradient solar pond. So, thank you very much for watching this video. Hope you have enjoyed this video.